In this presentation, we'll discuss transient response specifications. These specifications are often encountered in mechanical systems, especially ones that feature automatic control. These specifications are about how the mechanical system responds to a step input. Our first goal is to define these specifications, and then we'll turn to relating them to the pole location of second-order systems. To define them, we'll need to mark several points on the transient response. The first of these is the maximum value of the response, labeled Ymax. The second I'll point out is the steady state value to a step input, and this is labeled YSS for Y steady state. The time required to reach Ymax is labeled T sub P, or time to peak. We'll note several other points on the response, and we've labeled them. 10% of the steady state value is 0.1 YSS, and 90% of the steady state value is 0.9 YSS. We'll denote the time it takes to go from 10% of the steady state value to 90% of the steady state value as T sub R. This is the rise time. When the response has fallen between plus and minus 2% of the steady state value, we refer to the system as having settled, and we denote this time as T sub S, the settling time. Plus and minus 2% of the steady state value is the region between 1.02 YSS and 0.98 YSS. The settling time is the time at which the response enters this region and does not leave it afterwards. Here are the four specifications we'll discuss in this lecture. The first is the max percent overshoot. The second is the peak time. The third is the rise time. And the fourth is the settling time. On the previous graph, we saw all of these indicated. I should mention that the rise time is defined in different ways in different texts. Here we're using the time required to go between 10% and 90% of the steady state value. We'll now relate these specifications to the pole location of second-order systems. Our first specification is percent overshoot. The max percent overshoot is Ymax minus Y steady state divided by Y steady state times 100. And this can be related to pole location in the following way. Max percent overshoot is equal to 100 times e to the quantity minus zeta over square root of 1 minus zeta squared times pi. Here zeta is the damping factor of the second-order system's poles. And we know that lines of constant zeta are rays extending from the origin out into the complex plane. Since each ray of this kind can be associated with a unique zeta value, we know that no matter where a pole exists upon such a line, it will have the same max percent overshoot. Let's look at lines of constant zeta for 3 different zeta values, and then relate this to the max percent overshoot. Our first case, labeled 1, is a zeta value of 0. This is a system with no damping, and the poles are on the imaginary axis. For this case, the max percent overshoot is 100%. Our second case, labeled 2, has a damping ratio of 0.45. This corresponds to the blue lines emanating out into the complex plane as shown. If the poles are on these blue lines, then the damping factor will be 0.45, and correspondingly, the max percent overshoot will be about 20%. Our third case has a zeta value of about 0.8. This corresponds to a percent overshoot very close to 0. The poles would be on lines drawn in orange in the complex plane and labeled 3. That is, the poles are much closer to the real axis in this case than in the other two cases we've considered. The important lesson here is that max percent overshoot is directly related to pole location. The closer the poles are to the real axis, the lower the max percent overshoot, and the closer the poles are to the imaginary axis, the higher the max percent overshoot. Now let's turn our attention to our second transient response specification, that is settling time. Settling time is approximately equal to 4 times the time constant. And for a second order system, the time constant, capital T, is related to pole location in the following way. Capital T equals 1 over zeta times omega n. If you recall, the real part of a pair of complex conjugate poles in the complex plane is given as minus zeta omega n. So that tells us that the real part of our poles will be equal to minus 1 over capital T. That is, vertical lines in the complex plane are lines of constant capital T, time constant, and therefore are lines of constant settling time. Since the settling time is approximately 4 times the time constant, capital T, and since the real part of the poles is minus 1 over capital T, we know the following: that as the poles move farther to the left, the time constant will get smaller and the settling time will get smaller. As the poles move closer to the imaginary axis, farther to the right, the settling time will become larger. Now the settling time isn't precisely equal to 4 times the time constant. It's actually dependent upon the value of the damping factor, zeta. And so if we incorporate zeta into our analysis, we'll get a more accurate idea of what the settling time is. And this is shown in this figure, which shows settling time versus damping factor. And settling time is expressed in terms of the time constant, capital T. And you'll notice on the curve marked in green, which is the 2% settling time answer, that usually the answer is close to 4 times the time constant. But there are certain values of zeta where actually the settling time is less than this. While we'll typically approximate the settling time as 4 times the time constant, you should be aware that there are these special values of zeta where we'll do better than 4 times the time constant. Now we'll look at our third specification, that of rise time. And the relationship between rise time and pole location is much more complex than the other relationships we've studied previously. This curve shows rise time as a function of damping ratio and also undamped natural frequency, omega n. Now for a pair of complex conjugate poles, omega n is the distance the poles are from the origin. And we learned previously that zeta corresponded to a line emanating from the origin in the complex plane at a certain angle from the real axis. So, we can now make the relationship between rise time and zeta and omega n, that is between rise time t sub r and pole location. If we're given a pair of poles and we measure how far they are from the origin, omega n, and we determine the zeta for these poles, we can then turn to this graph to determine what the rise time is. On the vertical axis in this graph is the rise time times omega n, which is a normalized value of rise time, that is, it's unitless. And on the horizontal axis is damping ratio. From the curve given, one can determine the rise time if one knows the damping ratio and the undamped natural frequency, omega n. To show this, let's take a quick look at an example problem. So for our example problem, we'll have a pair of complex conjugate poles that are in the left half plane and that have a damping factor of 0.5 and are 10 radians per second away from the origin. And we want to find the rise time for these poles. Our first step will be to find the damping ratio of 0.5. Looking for where this intersects the curve, we'll find that it corresponds to a rise time times natural frequency of 1.65. From this relation, we can find the rise time. The rise time will be equal to 1.65 divided by the natural frequency, omega n. Since the poles are 10 radians per second away from the origin, we know that omega n is equal to 10. Solving for the rise time, we find the rise time is 0.165 seconds. Now we'll turn to our fourth and last transient response specification, and that is peak time. This is the time when the output reaches its maximum value in response to a step input. T sub p is equal to pi over omega d, where omega d, if you'll recall, is the imaginary part of the complex poles. So lines of constant omega d are horizontal lines in the complex plane. These are also lines of constant peak time. As the lines move farther away from the real axis, we'll get increasing values of omega d and decreasing values of t sub p. So peak time will decrease as the poles move away from the real axis. So we have introduced 4 different transient response specifications for the response of a system to a step input. These were the max percent overshoot, peak time, rise time, and settling time. And you've seen that all of these are related to pole location.